hydrogenation of alkenes. Hydrogenation of alkenes can be done by using catalyst in which hydrogen adds to the alkene, unsaturated double bond become a saturated bond. So we will be synthesizing an alkane mostly. So catalytic hydrogenation is the way to hydrogenate. Catalytic hydrogenation is the method for hydrogenation of alkenes. So H2 will be added to alkene. So alkenes are readily hydrogenated in the presence of under pressure in the presence of a catalyst. Under pressure in the presence of a catalyst. In the presence of a catalyst. There are two classes of catalysts that we have to discuss. Catalysts. Two classes. One is heterogeneous catalyst. Another one is homogeneous catalyst. Now we will discuss about these heterogeneous catalysts as well as homogeneous catalysts and which one is superior. That also we will discuss. Heterogeneous catalyst. They are insoluble in the medium. Insoluble in the medium. That is reaction medium. Example, Ranane nickel, palladium on charcoal, platinum metal, platinum oxide, rhodium, ruthenium, zinc oxide. These are all the examples of heterogeneous catalysts. Now homogeneous catalysts. Soluble in reaction medium. Example, chlorotris triphenyl phosphine, rhodium, called as Wilkinson catalyst. It's one of the very popular catalysts for homogeneous catalysis. Another compound is chlorotriphenylphosphine ruthenium 2. One more complex has been given, that is COCN5, pentacyanocobaltate, COCN5 3 minus. Now we need to look at which one have advantage. Of course, both can be used in different way. Homogeneous catalysts have always the advantage. Let us discuss the nature of these catalysts. Homogeneous catalysts have always the advantage. Homogeneous catalysts always have advantage, often have the advantage of better catalysts. Reproducibility of better catalyst, reproducibility, better selectivity, they cannot be poisoned. Catalytic poison is not possible. Catalytic poisoning are less susceptible On the other hand, heterogeneous catalysts are usually poisoned. Heterogeneous catalysts are usually poisoned. Poisoned by external, by other sources. Example, small amount of sulfur, will poison. Found in rubber stoppers can poison. Or sulfur containing compounds such as thiols, sulfides can poison them and they may undergo unreactive. So poisoning is possible in the case of heterogeneous catalysts. But heterogeneous catalysts have an advantage. They can be easily separated from reaction medium. Heterogeneous catalysts can be separated. Homogeneous catalysts can be separated easily from the medium. Can be separated easily from the reaction medium because they are insoluble in the reaction medium. Easily separable. You can say easily separated from the mixture, from the reaction mixture, Now let us look at heterogeneous catalytic hydrogenation. We will discuss homogeneous catalytic hydrogenation also separately. First we will discuss about the heterogeneous catalytic hydrogenation. finely divided platinum and palladium are the examples for heterogeneous catalytic hydrogenation, very efficient at room temperature. At room temperature. Most of the CC double bonds can be reduced. By these catalysts at temperatures below 100 degree centigrade and at atmospheric pressure. Atmospheric or slightly increased pressure. Example, malic acid. Platinum hydrogen can be reduced to succinic acid. Raney nickel is slightly less active. It's less active than platinum or palladium catalyst. So, but still, Raney nickel is used as a reducing agent. When it is used, the temperature for reduction is around 100 degree centigrade and approximately 3 atmospheric pressure. Most of the alkenes are hydrogenated using Raney nickel. Example, ethylene can be converted by Raney nickel and hydrogen to ethane. Example. Now we have to look at what kind of double bonds can be reduced easily. So the rate of hydrogenation of olefinic bonds at room temperature and atmospheric pressure can be, it's a monosubstituted, no? That is greater than disubstituted. This is monosubstituted, this is disubstituted alkene or a ring double bond. A ring double bond is also equivalent to a disubstituted alkene only. So a monosubstituted alkene can be reduced easily. So the rate of hydrogenation, we can look at like this. A monosubstituted reduced faster then disubstituted or a ring double bond. Suppose if there are tri-substituted and tetra-substituted, then the hydrogenation will be difficult. For example, R2C double bond or CHR, a tri-substituted olefin, or a tetra-substituted olefin. Hydrogenation is difficult. Hydrogenation is difficult. But it is possible at higher temperature as well as higher pressure. These tri-substituted and tetra-substituted olefin, first tetra-substituted olefin can be reduced. Tri-substituted double bond at 25 degree 100 atmosphere, at 25 degree centigrade 100 atmospheric pressure, under atmospheric pressure can be reduced. So pressure have to be increased in this case. Whereas in the case of tetra-substituted, it needs 275 degrees centigrade, very high temperature, and 1000 atmospheric pressure. So rash condition is needed for reducing the tetra-substituted olefin. So what are the double bonds that are very challenging to reduce? For example, the steroid molecule, a double bond that is common to two rings are very difficult to reduce. Example is steroidal substance. The molecule is given here. So this is the double bond. This is common to two rings. Double bond common to two rings. Difficult to reduce. Difficult to reduce. How these metal catalysts can be utilized? Metal catalysts are very expensive. Metal catalysts are very expensive, so they have to be absorbed over some support. So metal catalysts are expensive. They are usually absorbed on a support. Usually absorbed on a support. Usually absorbed on support. For example, support material. For example, support material of palladium on carbon as support. Carbon as support. Rhodium on alumina. So these two are support material. Support. The support materials have usage. What they does is They dilute the expensive metal. They dilute the expensive metal and assist in controlling. They dilute. Support material dilute the expensive metal. Controls the rate of reduction. Because there will be a diminished reactivity of the metal because of the support takes place. So there will be enhanced selectivity. There are many transition metals that are utilized for reducing the carbon-carbon double bond as well as carbon-carbon triple bond. So group 7 transition metal. That are useful, that have order of reactivity. Rhodium greater than iridium, that is greater than ruthenium. It is a decreasing order that I am writing. Iron. So among all, rhodium is more reactive. Rhodium is most active catalyst. In the series. Example for palladium charcoal reduction is given below. A cyclohexene upon reduction using this one gives a cyclohexane. Mechanism of reduction. Heterogeneous catalytic reduction. Adsorption process needs to be considered for viewing the mechanism of heterogeneous catalytic reduction of alkene. This is the metal surface where first hydrogen, this is catalyst surface. Hydrogen comes and sits on the surface. There is adsorption of hydrogen takes place over the catalyst surface. Catalyst with H2 adsorbed. Now, the pi orbitals of alkene will be attaching over the metal surface. Pi orbital. already two hydrogens are, already hydrogen is there in the metal surface. This will come and set over the metal surface. Just a bond only. Next step only is the catalyst with H2 and alkene both absorbed. Alkene absorbed. Now the hydrogen will be transferred to the alkene and desorption process takes place. That is, freed alkene will come out of the catalyst surface. So here catalyst and product, freed product that is coming out, the freed product you can see. This is the mechanism. So one phase of the alkene double bond will be absorbed over the metal surface. Then the hydrogen that is already absorbed is there will be transferred to the alkene. Thereby reduction process gets completed. And at last, after the reduction, the freed product, that is alkane, is coming out of the catalyst surface, and catalyst is once again ready for further reducing purpose. Now we have to look at the stereochemistry of this reduction, heterogeneous reduction, stereochemistry. Stereochemistry of heterogeneous reduction. Stereochemistry of heterogeneous reduction. It is predominantly syn addition. Stereospecific. It is stereospecific syn addition. So same phase of the double bond. Hydrogen adds to the same phase of the double bond. Hydrogen adds to the same phase of the alkene. Example. This is 1,2-dimethyl-cyclohexene. Hydrogen and platinum upon reduction gives cis product in 80%. Cis 1,2-dimethyl-cyclohexane, and trans is forming in 20%. Trans 20%. Of course, trans product formation is there, but it is predominantly a syn addition and stereospecific. This is with hydrogen and platinum. In the presence of palladium, actually the compound undergoes isomerization. In the presence of palladium. leads to a trans product because of the isomerization. Trans product will be the predominant product. Platinum is also used in the form of platinum oxide called as Adams catalyst. PTO2 called Adams catalyst. Adams catalyst. Is used for reduction purpose, is used for catalytic reduction. During the process, PTO2 will be reduced to PT and it will be catalyzing the reaction. Example is there. Cis product will be predominating because it is a syn addition. This will be 80% approximately cis, plus trans product of course will be 20%. Rings, rigid ring system are quite interesting molecules. Depending upon the nature of the nature and position of the substituent, the reduction gives cis and trans mixture. Let us look into that. For example, cholesterol, rigid ring systems, rigid ring systems. Rigid ring systems, we have to look at the hindrance, whether the substituent that are there, whether it hinders the molecule for absorption, thereby reduction will be affected or not, we have to check. Example cholesterol, So this is the angular methyl group. There is a double bond here. Containing X as a substituent, We know already usually when it is going to absorb in the metal surface, hydrogen first absorbs, hydrogen absorbs, then this will be absorbing. I am not writing the orbital structure here, but you have to assume there is an orbital, pi orbital, that is actually absorbing on the metal surface. This anchoring group doesn't allow from that particular side to absorb. So this is the only possible path that this can absorb on the catalyst surface, and the substituent X must be equatorial. That is important requirement. Then the reduction process occurs, thereby hydrogens can be added. So this is that we usually write for the steroidal system. Its continuity is there. It's a cholesterol derivative like that we can look at. Now this anchoring methyl group will be there and substituent X will be there. It is 80%. Suppose if X is axial, then it's very difficult for the molecule to fit to the catalyst surface because it is hindered from both the sides, because of X from this side and because of anchoring methyl group on that side. So there will be a mixture of cis and trans. Cis and trans products. In trans decadent system, forms as products. Incomparable amounts. Another hydrogenation method is there. It is called as transfer hydrogenation. In this transfer hydrogenation, one molecule will transfer its hydrogen to another molecule in the presence of transition metal catalyst. Thereby, the molecule that is transferring the hydrogen gets oxidized, and the molecule that receives the hydrogen gets reduced. That is what that we have to look at. Example, in the presence of palladium catalyst, the reaction of an alkene with cyclohexene. Two molecules of alkene, because the cyclohexene can transfer two molecules of hydrogen itself. So two molecules of alkene in the presence of palladium catalyst, palladium carbon, two molecules of alkane plus benzene is uptime. Benzene is uptime in this case. This is about heterogeneous catalyst. We will discuss next a homogeneous catalyst and its mechanism.